Thank you for taking your time for my session. What is ML Ops? I'm Kaz. I'm a developer advocate, so it's like an evangelist for developers. I usually attending many different public events and meetups like this, and talking about the products and technologies from Google, focusing on the machine learning, data analytics products such as TensorFlow, BigQuery, and Cloud AI. I have been working at Google Tokyo office for over 8 years. So what is ML Ops? How many people have heard ML Ops, the word ML Ops? Almost, only a few people, like 5, less than 10 people. Because this word is not popular yet. But there are many other similar words like SysML or the OpML or any other things. Because, yeah, the concept is quite new. So let's learn what is ML Ops. And the reason why I have started talking about ML Ops, it was about 2 years ago. Last time 2 years ago when I had a session at Next San Francisco, Cloud Next San Francisco. That is another largest event from Google. And the reason was that I had a conversation with a software engineer at Google who has been supporting maybe the largest machine learning infrastructure inside Google for over 12 years. And he said, launching the machine learning system is the easiest part. The operating that machine learning system for many years is the hardest part. The real problem with the machine learning would be found while you are continuously operating that for like 5 years or 10 years. Not many people have been operating the machine learning-based systems for over 10 years, but Google did that. And we have collected many different learnings and practices to do that. So we thought that the idea of DevOps could be also applied to the machine learning-based production systems. What is DevOps? I have copied this text from Wikipedia. So yeah, DevOps is all about unifying the development and operations, Dev and Ops, by strongly advocate automation and monitoring of the whole system. And we can use the same concept on the operating the machine learning-based systems. So that is the meaning of the ML Ops, DevOps for ML. So it's all about unifying machine learning systems development and operation by automation and monitoring of the whole systems. And the topics I'll be covering with this session is based on the 2 great papers. So if you're interested in those ML Ops topics, please take a look at these papers. The first paper is I call it a technical debt paper. Machine learning, high interest credit card of technical debt. So it's kind of the bad feedback on building the machine learning-based systems. You may want to avoid using the machine learning for production systems. That is the concept of this paper, but it's really valuable, worth to take a look at. And this is written by the software engineers at Google who has been building the AdWords machine learning-based infrastructure for many years. And there's also another document, publication called Rules of Machine Learning. This also provides the very good examples of and best practices for operating the machine learning in production. So I was so impressed with the topics and the concepts covered by these publications. And so that was the reason why I have started talking about ML Ops in these sessions. And I will cover the many anti-patterns and solutions for those anti-patterns for development phase, deployment, and operation phases. So let's take a look at the first anti-pattern, that is an ML superhero pattern. I have seen those ML superheroes in many large enterprises who are trying to bring the machine learning into production. Because the enterprise has many talented, excellent people, they could have a couple of people who can do everything by himself or herself. Like the superhero can be ML researchers who are making the machine learning, the papers all the time. They understand what's going on with the mathematical formula and the equations, and write it down with the Python code on the notebook. And also, the superhero can write the Apache Spark code, Hadoop code, or BigQuery, the Redshift code as well. And if needed, the superhero can build a production, the ops, and the infrastructure system by itself. And also can talk with the business people as a product manager, can talk with the CXOs, CTOs, and explain what's happening in the machine learning system. And this is a great person, but the business operation doesn't scale. So many large enterprises could have tens of hundreds of different the possible machine learning production projects. And only a single, like a few projects can be covered by that kind of superhero. So if you're really serious about bringing the machine learning or deep learning into the businesses, real-world businesses of the enterprises, this ML superhero pattern doesn't work, doesn't scale. So solution is to split the roles into the multiple roles and the steps in the team. And you have to build a scalable team with the ML researchers, data engineers, ops people, PM, and business decision maker. Let's take a look at the video as one example.
Awesome. Okay. All right. So click on that and speak into the mic.
May I have some gum?
So it understood what you said. May I have some gum? Now it's going through natural language processing. It's identifying the noun there, and gum. So now it's trying to. It will then match based upon the model that's been modified. Come on, come on, come on. And it is picking chewy gum. Oh, and there the camera identified extra long-lasting watermelon gum. Now the camera's and over, and there's your gum.
That's great.
Machine learning in an app.
So I get to keep this, right?
Yeah, actually I've got like 7 boxes back there, so please take everybody.
So that was the demonstrations we have shown at the Google I/O 2 years ago. And I built this as a production manager. And I was able to find a great vendor who built the whole scalable team with the ML researchers and engineers and the production managers. So there was a researcher who wrote the TensorFlow code to apply the object detection model on the image recognition, and also uses the machine learning APIs from Google Cloud for the voice recognition and the what else? The word-to-vec model to understand what the requests of the user. So that word-to-vec models can understand the distance between the words like sweet and hot and spicy and so on. So that they were able to integrate the whole systems. And also there were other engineers like a software integration engineer and also hardware engineer who hacked into the robot SDK to control the robot arms. And project manager who keep reporting the status of the projects to me. And I was the business decision maker. And I was talking with the amount of people, marketing people about the budget and the quality of the service and so on. So this was just a demonstration, but for me, it was a production system. I didn't want it to have the demo have a huge serious trouble during the events. So my vendor did a great job on building a scalable team so that we were able to bring these same demonstrations to the other venues and the events, like CloudNext 2 years ago at San Francisco and Tokyo and so on. And I hadn't to be there on site all the times because the team was scalable so that the vendor was able to assign a different people for the different regions like Tokyo and San Francisco. Another anti-pattern is so-called black box patterns. And if you have a researcher who wrote the notebooks, and if you have an engineer who brought the notebook into production, in many cases, without any caution, the things like the black box can happen, where researcher doesn't understand what's happening inside production code, but the engineer doesn't understand what's happening inside the model itself. What are the reasons why the researchers used this kind of TensorFlow code to build this system? And technical debt paper says at Google, the hybrid research approach where engineers and the researchers are embedded together on the same teams, that helped reduce this source of the friction significantly and avoid the black box problem. And one example to avoid that kind of the black box problem is to share the same platform with the researchers and the engineers to build a scalable systems from scratch. And the product is called a Cloud AI platform. we have changed the product name from ML Engine. That was called Cloud ML Engine before, but now we call it as a Cloud AI Platform. And Cloud AI Platform allows you to use a fully managed, scalable training and prediction infrastructure, and that supports the TensorFlow and XGBoost scikit-learn. So rather than using the data scientists, local machines, or any specific virtual machines, the data scientists and the engineers can share the Cloud AI platform, where they also share the notebooks to build the scalable infrastructure. Let's take a look at the video. So this is a sample notebooks where the data scientists can start using the scikit-learn on the Jupyter notebook. So this is a usual scikit-learn code that people will be using. You can execute the BigQuery SQL to download the data from the data warehouse and use the usual scikit-learn APIs to do the data preparation, such as splitting the data into a training and test data set. And also, at the next cell, it is defining a pipeline of scikit-learn to define some pipelines for the data training and call a fit function to train a model. So this has been a usual, ordinary scikit-learn code the data scientists would write. And then that notebook could be shared with the engineers who can bring the model into the production running on the AI platform. So you can see it is using the Google Cloud ML Engine command so that they can bring the same scikit-learn model running on the Cloud AI platform, which is scalable and fully managed. And it's production ready already. So this could be the solutions to avoid that kind of the black box problem and the lack of scalability. So another anti-pattern could be change anything changes everything, or CACE. So this is caused by the entanglement happening inside ML system. Because I suppose many people have experience on running the usual web-based systems or non-machine learning systems. But if you are bringing the machine learning model in your systems, there could be some things unexpected happening in the production or while operating. Because everything in the usual IT systems is written with the code written by humans. So everything should be expected. But machine learning-based systems is driven by the data. Your system behavior is defined by data, not by your code. So sometimes the humans don't understand what will be happening inside it. So that's the reason why the software engineer says it. The launching is easy, but the operating is hard. Because while you're operating the machine learning-based system for many years, a slightest change could be happening, like changes in the hyperparameters. Hyperparameters means the things like how many layers in the neural networks you would use, or what would be the way of pre-processing, or for the data processing, or what would be the learning rate. So those smallest changes in those parameters could change the drastic changes in the system behavior. That is called CACE. And the ML paper says rule number 14, starting with an interpretable model makes debugging easier. And also, if you are using ensemble-based systems, keep ensemble simple so that it's going to be easy to debug. So use simple model rather than the complex deep model. So now it's the AI is booming. So many people like to use the deep learning model compared with the other traditional models such as linear regression or linear models, so that you can make your resume shinier. But it's really risky to use the deep learning model because sometimes deep learning model could be a black box. It's really hard to debug it. For example, the linear model or linear logistic regression could be so-called convex model. So it is guaranteed to get the optimal result, optimal training, the accuracy, every time you try to train the model. Whereas the deep model is so-called non-convex. It behaves so complex while you are training. You may remember that there will be a very complex patterns you can see on the loss changes while you are training a model. So anyway, it's not guaranteed to get the optimal result for every time you train the model, deep learning model. So if you do, you can do the same thing with both deep model and simple model. It's better to choose the simple model because it's much easier for the ops people to debug it. And also, it's many cases it's can be easier to interpret it by the humans. Also, in many cases, people sometimes tends to use the giant monolithic model, deep learning model that takes hundreds or thousands of features and provides the best prediction result from the big deep learning model. But if possible, you may want to split the big model into a bunch of the smaller model and make an ensemble model out of it. So it's just like building a parts factory, small parts factory, and building one big assembly plant that takes all the outputs from those small parts factory. So that makes you much easier for the debug and troubleshooting in the production system and make it semantically interpretable by humans. Otherwise, if you have one giant monolithic model, deep learning model, sometimes it gets one big black box. It's really hard to what's happening inside it when you are having a trouble with the system. Take a look at some example. This is the system, image classification system built by a used car trading company in Japan. And they are the largest auction service for the used cars in Japan. And they have built the TensorFlow-based image classification system only for the used cars. And they have been operating this system for 2 years already. And they have started building these systems by using one giant monolithic deep learning model. But that was really hard to do a troubleshooting and make any improvement on the system. So instead of the monolithic model, they have split the model into a bunch of the smaller model. A model that identifies car parts, a model that identifies the car angle, or identify car maker, car name, model, and pricing, and make an ensemble by using those the features. So that made this vendor really easy to debug and do the troubleshooting, and also makes the improvement on the whole system. So let's take a look at another anti-pattern, lack of data validation. Why this is an anti-pattern? Because this is the significant change from the ordinary IT system to the machine learning-based system. In IT system, everybody writes the code, programming code, to define the behavior of IT systems, so that you are able to write the maybe tens or millions of the unit testing code with the CI/CD systems and make sure the system is working as intended, because everything is written by humans and defined by humans. But with machine learning system, as I mentioned, the behavior of the system is defined by those bits and data in the machine learning models, not by the codes. And sometimes the systems can give you some unexpected behavior, because the behavior of the system is defined by data, not by code. But what kind of the unit test tool? Can you use the JUnit code to define or guarantee the behavior of your machine learning-based systems? So actually, not many people are using the unit testing or regression testing or the machine learning or checking the machine learning behaviors. And also, there's another problem called the training serving skew. This is changes of or dropping down of the accuracy, the real accuracy you'll be getting at the serving infrastructure. When you are training the model on your Jupyter notebook, on your cloud, or on your local, maybe you are getting a really great accuracy. But if you bring the same model into production system, somehow your accuracy will be dropping down significantly. This happens many times. And this is caused by any changes on the training data itself, or the way of pre-processing, or the definition of the window in a time series, and everything. Subtle change could drop the accuracy in production system. The solution could be a TFX, TensorFlow Extended. So TensorFlow is the framework, open source framework for training and prediction and developing the machine learning model. but TensorFlow covers only a small fraction of the whole production system. This is the part where you can use TensorFlow. But if you want to bring the machine learning into production, you have to build everything, starting from the data ingestion, collecting data from data warehouse or database, and make a data validation, and also the transforming the data if you need it, and train that with TensorFlow. And after that, you have to make sure that your model works as intended by model analysis. And you have to build the serving infrastructure. You can use the Kubernetes cluster on Google Cloud or maybe AWS, or you may want to build your own serving infrastructure anyway. And also you have to do the logging. Everything is required. And also you have to have the orchestration tool of the whole machine learning pipeline. And TFX tries to cover the other components other than the TensorFlow itself. And one of them is the TensorFlow data validation, or TFDV. This helps developers understand, validate, and monitor the machine learning data, training data at scale. And this tool actually has been used by the internal teams like a Google Play team or YouTube team with the petabytes of data at Google every day. So this is a proven tool. And so that those teams were able to use TFDV to maintain the health of the production machine learning pipelines. TFX also has a paper, so this is another recommended publication. TFX paper says we want the user to treat data errors with the same rigor and care that they deal with bugs in code. So as I mentioned, data is the code in machine learning systems. So just like the bugs in your code, if you have any troubles, not troubles, but any significant changes on the distributions or patterns in the training data, that should be treated as a bug in your code. And actually, by bringing the concept of the data validation into production, Google Play team was able to increase the application install rate for 2% by finding this tail table. Let's take a look at how the TFDV works. This is another Jupyter notebook that uses the Chicago taxi trips data as a training test data set. And you are writing the BigQuery SQL to download the Chicago taxi trip data set from the data warehouse to the notebook. And this table has the records such as the trip timestamp on what is the cash payment, the payment types, and so on. And by using a TFDB, you can easily visualize what's happening inside those training data. Take a look at those statistics by looking at the histograms and the distributions. For example, by looking at the payment types, it seems like many people are using cash or credit card as a payment type. And if you have any changes or any the troubles in the training data set, you can easily find out on these visualizations. And also you can define, you can also use the tool for sees the changes of the training data and the evaluation data. Even if you are getting the bad result with the evaluation data, many cases, or sometimes it could be caused by the difference of the distributions of the training data and the evaluation data. So by looking at the visualization of the TFDBs, you can easily find out, because they are using the totally different data sets with different distribution, that could be the reason of the degraded accuracy. And also, for the training serving skew, TFDB can help you on finding many different skews, like a schema skew, feature skew, distribution skew. So you will see the tables with the reports that has payment type feature has some problems, and that could cause the training serving skews in production. So this is the things you may want to do before training, validating the distribution of the training data set. And after training the model and using the model in productions, there could be another bad practice or anti-practice called lack of continuous monitoring. So because this is an SREcon session, so many people likes to have many different dashboards and ways to do the continuous monitoring on the other metrics other than the machine learning behaviors. But what about the behavior of the machine learning model itself? What about the accuracy of the machine learning model? there hasn't been has not been so many tools for the keep tracking the machine learning performance. So data scientists are interested in the building a POC or prototypes or notebooks, and they got the great accuracy result on the notebooks and was able to bring the notebooks into production. But after 1 or 2 or 3 years, the dot accuracy could be dropping down. And any kind of the machine learning model could be stale over time. That could be a few years, 1 year, or a few quarters, or months, or weeks. But anyways, eventually your machine learning model could be stale, and you'll be seeing a dropping down of the accuracy. At that time, if the end user could be the first people who notice the drops of the accuracy, and the business people would notice that, and your director would ask you to update the model ASAP. So you have to find out the Jupyter notebooks you have written 2 years ago and rebuild everything from scratch in a hurry. And you also want to know the refreshment requirements before building your machine learning systems, because each business requirement has a different requirements for the freshness. For example, news aggregation sites, if they are using the machine learning models, they may want to retrain the model for every 5 minutes or every 10 minutes. Or if it's a recommendation system for the e-commerce website, then maybe it could be just every day or every week to retrain the model. Natural language processing or voice recognition doesn't require much higher frequency on the retraining. But anyway, you have to know that. What would be the frequency you have to rebuild the machine learning models? So ML paper says, know the freshness requirement of your systems. And the solution for that problem is the TFMA, TensorFlow model analysis. This is about after training the model. If you got your model trained, you can use the TFMA to validate the behavior of your systems and check whether the model accuracy is dropping down or not. So, and also by using TFMA, you can specify any quality thresholds, and you can make sure that it behaves as expected. For example, by using the TFMA, you can easily draw a graph on the TensorBoard, which is a user interface for the TensorFlow, and compare the different accuracy over time. So if you have the version 1 model, but version 2 or version 3 model that could have the worst bad accuracy. You can see it easily find the accuracy dropping down over time. Also, with the TFMA, you can define a slice and compare the slice between the accuracy between those slices. By slice, I mean the different segment in a training data set or serving data set. For example, you can define any arbitrary slices based on the geographic region or the any demographic differences of the users, anything. For example, this model works so well on the people in the United States, but doesn't work so well on the Asian people. Why is that? By using TFMA, you can define slices for the geographic regions, EU or US or APAC, and compare the accuracies between those regions. And you can apply the definition of slices to other definitions, like the ages and the male, female, and everything. So let's take a look at another example of how TFMA works. So in these notebooks, it tries to import the TFMA. By the way, everything is open source, so you can download and try it by paying anything. This is about TFX, which is an open source tool, not cloud AI product. And once you have defined the everything's configurations, like directories of the model and the data you have stored on the Google Cloud Storage, then you can draw a chart like this, where you can print show all the different metrics, such as what is the count, how many records in a specific slice, and also you can choose the different metrics from the menu so that you can find out what's the accuracy changes over time. Maybe your model works so well at noontime, but doesn't work so well at midnight and things like that. And by using TFMA, you can also check out what's the behavior against the in how can I say that? You can also check the ML fairness aspect of your model. What is ML fairness? ML fairness is about the fairness on the different cultural differences or the male or female or regions or any differences, and how the machine learning performance for different the segments of the users. For example, at Google's Quick Draw project, we have asked many people, different people, to draw a picture of shoes with handwritten drawings. And many people tries to write the pictures in blue type, this kind of shoes. But this kind of shoes also should be classified as the shoes. But if you collect the data sets and use it as is, many cases that kind of the natural data set has some biases. Biases caused by those regional differences or cultural differences. So if you want to bring the machine learning system that could be used by many different regions and cultures, you have to check the data behavior of the model by using the ML fairness tools. And the TFML provides the fairness indicator so that you can define a slices between those cultural differences or the ages or male, females, and so on. So you can make sure that your model has a certain diversity on its behavior. Lastly, I'd like to talk about the ML lifecycle management. And in many the cases, data scientists starts project without the concept of the lifecycle management, so that the data scientists would start writing the notebooks and with the training data set and would get the really great accuracy and bring that notebooks into production as is. Or maybe engineers can help that to build a scalable system. But in many cases, that data scientist could be a point of contact in case of emergency. And so that the data scientists or ML researchers have to do emergency planning by fixing those notebooks or retrain the model, everything. And they don't want to avoid that situation. This happens because of the lack of the machine learning lifecycle management. If we can build a machine learning lifecycle management with machine learning pipeline, then we can split the roles into the machine learning engineers and machine learning ops people and the business decision maker so that we can avoid this problem. As I mentioned, there are many different components like ingestion, analysis, and training, validation, and serving, logging. This is the whole suite you require to build a machine learning production system with the lifecycle management and pipeline definition and orchestration. And to build this kind of orchestration setup, we provide Kubeflow pipeline. Kubeflow is a technology that allows you to define a container that does the machine learning task inside the Kubernetes cluster. So we are putting a significant development resource on building, doing every machine learning tasks on Kubeflow, Kubernetes and Kubeflow. And now we have Kubeflow pipeline. With that, you can easily define a machine learning pipeline by stitching and connecting various components like building blocks. Kubeflow pipelines allows you to containerize everything, like ingesting data and transforming the data, validating data, and training the model and validating the model. Everything could be defined as a container on the Kubernetes or Kubeflow. And you can use a Python DSL to define a machine learning pipeline. And you can define the sequence of those tasks, or if you can do it, we can make parallel execution of each task. And it provides this kind of the UI, so you can easily find out what's happening inside it, what has happened in the past training. Starting from the data validation and data feature engineering, that the features could be shared among the parallel training tasks. And also you may want to use the TFMA to do the validation of the trained model. And you can push the model into production setup. And also you can easily compare the different analysis results. Take a look at some example.
Executed runs. So if we click on this run, this is a completed run. I can show you some of the functionality that Anand was speaking about earlier. So one of the interesting things that we can see is, of course, the inputs and outputs to each step, but also the output artifacts that are available to you. So one of the output artifacts that we have available to us here is at the evaluation stage or step is an ROC curve. So as an end user, you can easily drill into this curve and evaluate the performance of the specific run. But just doing this on a single run is not really that interesting. It's useful, but a more powerful way to do this is to look at multiple of these runs together. So we can actually click on multiple of these runs and compare them together. And you can see that the only thing that varies here is the input parameters of the list of features. So here we have more or less features for each of these runs. Everything else is constant. So what Kubeflow Pipelines does is it actually shows you the output artifacts at each stage that has the same name, but it also shows you an aggregated view. So here you get an aggregated view of all three of these runs. So you as a user can drill into the performance of these runs and compare and contrast them. So if you're spinning up many pipelines, you can quickly compare them. And even end users that are not developers can quickly compare them.
As you can see, so by using Kubeflow Pipelines, there's a UI where you can easily compare the performance results from the different ML pipeline runs. So you can easily compare and find out the accuracy is dropping down, so that we have to roll back the whole pipelines, whole model to the previous version.
And some more of the pipeline artifacts, output artifacts that I want to show you is captured in a TFX pipeline here. So this is a bit more of a complicated run. It has more steps to it. So this is using the New York City taxi data, and it's a TensorFlow model that it's training. So some of the other artifacts that can be produced, for example, is a confusion matrix. So this matrix.
So yeah, confusion matrix is one of the popular ways to check out how your machine learning model behaves. So this is the expected result, and these are the predicted result, and you can easily visually looking at what's the performance of your model.
It's great for quickly analyzing a classifier. We've also got a table, which is a very practical thing to expose to end users. You can just quickly get a sample of data and expose it to the end user. They don't need to open up BigQuery or any kind of CSV file on GCS. One of my favorite output artifacts is just a static HTML. As an engineer, this unlocks a lot of doors because now we can embed.
Yeah, as I mentioned, the TFMA, the matrix, slicing matrix, can be also integrated within Kubeflow pipelines. So the ML ops people can actually use the TFMA to make sure that your machine learning models is working as intended.
Any HTML and JavaScript and render anything within Kubeflow pipelines for our end users.
So that was the anti-patterns and the solutions I wanted to mention. So as a summary, let's what are the anti-patterns and solutions? So for development phase, we may want to avoid the superheroes who does everything. Rather than that, we may want to split the roles to build a scalable team. And we have to share the same notebook or any artifacts with all the stakeholders. Researchers and engineers and ops people should understand what's going on inside the code. And you have to be careful CAC or change anything, change everything, because it's a special behavior you can see only in the machine learning system. In the deployment phases, you have to avoid those emergency programming done by the data scientists. So this is a role for the SREs and the ops people. And also you have to be careful about the continuous monitoring of the behavior or accuracy of your model, not only the usual statistics of your IT infrastructure. And to do that, as a business aspect, you have to understand what is the basic fundamental refreshment requirements of your machine learning model. And TFMA, TensorFlow Model Analytics, can help you to implement that. And if you're interested, please take a look at the great publications from Google and other people, so that you can find out all the other interesting discussions. So that was it. Thank you. And I have many times, so we can take many questions.
If you're going to ask a question, please use one of the microphones on the side so that we can get it in the recording.
Anything? Anything from the like the basics of machine learning or everything? Yeah.
Hey, so as systems get very complex, and as think about systems such as like Google Ads, you might see a user hit many, many different machine learning models. And when we want to test a newly deployed machine learning model, we'll probably canary it to a certain percentage of users and then look at the delta between results. But because the system is so large and there's so many models in play, it can be very hard to distinguish, like, is a user doing better because of one model or because of another model? A single user will hit many, many models. And if one is causing a really bad experience, diagnosing which canary or which model is causing issues can be very hard. Do you have any comments or thoughts on like how we can scale up the canary and new model validation process?
So the question is how we can scale up the canary, you mean?
When we deploy a new model, like as we get more models, the signal may become weaker and so on and so forth. Do you have any thoughts on like how we can continue to validate new models as the systems become more complex?
Yeah, actually, I cannot answer. I don't have any clear solution on that. And yeah, maybe many people are trying to find out to build a new solution for that because this is a quite new problem. And we were able to develop a base tool, but we need to have more and more practice to how we can use that. Yeah.
Cool. Thanks.
Thank you.
Yeah, I have a question here. Like we have, so data researcher builds the model and then the engineer does the development of applications. So they integrate it, right, through REST API or through PMML format. When it is Java, they do it through PMML integration. So is that a deployment, whatever you said, right, the TensorFlow deployment open source will take care of that integration as well?
Integration of what kind?
The model with the application.
Model and application. TensorFlow right now only provides the serving component. So the integration with the application is taken care by the users and developers. And there's another product called the AutoML from Google Cloud AI. That is a commercial product that takes care of everything. Okay. For example, by using Cloud AutoML, you can train your visual recognition model or translation model from scratch. And then it can automatically build the production serving infrastructure for yourself. And it provides the REST API to use that. So it provides a much, much higher integration with the applications than using the basic TensorFlow serving system. But anyway, the Cloud AI AutoML tool provides the REST API. So after that, you have to use the REST API to integrate that with your own application.
Okay, thank you.
Okay. Any other questions? Okay, I should be hanging around here for a while, so please directly come to me and ask any questions if you have. Thank you so much.